Experiments confirm that the number of decays per second is proportional to the total number of atoms. The more atoms there are, the more decays. And that decay is governed by the decay rate, which is called lambda. So the number of decays per second equals lambda times the number of atoms. Now the number of decays per second is essentially the rate of change of the number of atoms with time, or dn by dt, and that equals lambda n. We put a minus term in here because the rate of change is decreasing. We can rearrange this formula to read that dn over n equals minus lambda dt. Now if we integrate both sides, the integral of 1 over n is the log of n, and the integral of lambda dt is minus lambda t plus a constant. We can now put all these terms up as exponentials. The exponential of log n, of course, is simply n. The exponential of this term is the exponential of minus lambda t plus c, which can be written as e to the minus lambda t, e to the c. At t equals 0, in other words, at the start of the process, n is the original number of atoms, which we will call n0. So when t is 0 in this formula, we find that n becomes m0, e to the minus lambda t is e to the minus 0, which is 1, times e to the c. And therefore we get that n0 equals e to the c. And now we can write that n, from this formula here, n equals e to the c, which is n0, times e to the minus lambda t. This becomes n over n0 equals e to the minus lambda t, or, turning everything on its head, n0 divided by n equals e to the plus lambda t. Now let us consider what happens when n0 divided by n is 2. At that point, n is half the value of n0. In other words, we've got half of what we had at the start. In those circumstances, 2 equals e to the lambda t half. In other words, t is the time that it takes for the number of atoms to go down by 1/2. Now we can take logs of both sides, and we get that log 2 equals lambda t to the half. And that means that t to the half, which is the half-life, is log 2 divided by lambda. And that's the way of calculating what the half-life is. It's log 2 divided by the decay constant lambda. So what does this decay look like? This is a chart which shows the number of atoms along this axis and the time in seconds along this axis. Let's suppose that at the start of the process, when t equals 0, there are 400 atoms. And let's suppose the half-life is 10 seconds. What that means is that after 10 seconds, there will be half as many as there were before. There were 400, now there are 200. But after a further 10 seconds, there will be half of 200. So after a further 10 seconds, there will now only be 100 atoms. After a further 10 seconds, there will only be half of what we had before. So now there will only be 50 atoms. And after a further 10 seconds, there will only be half of what we had before. So now there will be 25 atoms. And so the chart looks like this. It's a decay curve. In practice, it's very difficult to count the number of atoms which are still remaining. So typically physicists count the radioactivity, which is the number of radioactive emissions, for example alpha or beta particle emissions. When the number of emissions halves, that tells you that the number of atoms has halved. What is amazing is that this decay is entirely random. You cannot predict which particular atom will decay. It's amazing that half the atoms will decay in a half-life, but half won't. Some atoms might decay in the first minutes or seconds. Others might not decay for thousands of years. All of this is governed by the weak interaction. The weak interaction is so called because it's weaker than the strong interaction, which is the nuclear force which holds the nucleus together, and the electromagnetic force, which is the force which tends to drive protons apart. Quantum mechanics tells us that the forces, in this case the weak interaction force, is a result of what's called exchange bosons or gauge bosons. In the case of the weak interaction, the gauge bosons are the Z or the W plus or minus gauge bosons. They are very heavy, and consequently the weak interaction is a very short range, and that means it's much less likely to happen. And that's just as well, because the sun works by the weak interaction. Protons are converted into neutrons. 2 protons and 2 neutrons, by various means, can form helium plus energy, and it's that energy that the sun radiates. But the weak interaction means that protons that are on the sun only rarely, given the number that there are, convert into neutrons. And that means that the sun can last for 10 billion years. It's currently about 5 billion years old, so it's halfway through. So the slow rate of the weak interaction is the reason that the sun doesn't convert all its hydrogen into helium in a very short time, and that's the reason why life can evolve on Earth.